Hello and welcome to the knowledge area of operating systems and virtualization security. My name is Herbert Bos. I'm from the VUSAC System Security Group at Vrije Universiteit Amsterdam. What I'm going to talk about is the security of operating systems and virtualization technology, and after a general introduction of what we mean by that and what we mean by different security domains and the relevance of security at this level of the software stack, I'm going to talk about different threats that we encounter at this level. How can attackers compromise the security of the operating system or the security guarantees offered by the operating system? And that will be partially related to the design of the operating system. How do we organize the operating system? Do we make it a single monolithic blob of code, or do we partition it in smaller components? And what is the relation of that to the well-known security principles that tell us how to make a system secure, as well as to the access models to the data and files and what have you that form the resources in a system. Okay, and then I'm going to switch gears and talk about different primitives that we can use to guarantee the isolation and the between different security domains, as well as the mediation of accesses across these domains. And I'm going to tell you about techniques to harden operating systems, making them harder to get compromised by attackers. And the final two things that I'm going to talk about are, how the issues and solutions that we find in operating system and hypervisor security have an impact on the related areas, such as, databases and what have you. And how easy, or rather how hard it is to get security solutions adopted in an operating system environment. But first, as mentioned, I'm going to give a general introduction about what kind of security are we talking about, and also a little bit of the history of this security, and specifically what has changed. It's good to realize that operating systems and virtual machines have been around for a long time, and much of the groundwork that we're going to talk about in this larger presentation was done in the 1960s and 1970s, when operating systems such as Multics, which had a huge influence on modern operating systems, were developed with security in mind from the beginning. And the reason for this was that the world changed in how we use these expensive computer systems, where they had been more, special purpose, mostly single purpose in the past. Now they became more and more multi-user, having multiple security domains, users with different access privileges. And they had to be able to work with this machine at the same time without jeopardizing the integrity or confidentiality of the data. And so much thought was put into thinking about how we design a secure system, principles and security primitives that were needed to maintain the security of the system. And operating systems such as Multics, often together with the hardware, started incorporating these security principles into working systems. And while Multics has died and has never been very popular to begin with, it has had a tremendous influence, and many of these security principles, primitives, and ideas live on in today's operating systems, such as Unix-based operating systems, Mac OS, and Windows. And what I'm going to argue is that in security at this level, much has stayed the same. Right? In the old days, the security was mostly concerned with isolating different users from each other, classes of users from each other. And this translated into, isolating processes or virtual machines. Now, today, we still isolate at this level. We still isolate processes and virtual machines. So this has stayed the same. Moreover, the principles that were pioneered in the 1960s and 1970s still apply almost without any change in today's systems. What has changed is that, well, first of all, we have a few more security domains than we had in the past. as we shall see. And moreover, we've seen a tremendous advance in the threats. So the types of attacks and the ways of attacking, the mechanisms and the attack vectors have evolved tremendously. And because of this, the operating systems and virtual machines have had to incorporate more and more advanced defenses also. In this presentation, we've already mentioned security domains a couple of times. It's time to make this more concrete. What we're talking about are multiple mutually non-trusting security domains, security environments, chunks of code that are executed. For instance, different processes need to be isolated from each other. The kernel needs to be isolated from the processors and needs to ensure that the processors are isolated from each other. The hypervisor needs to be isolated from the kernel that runs on top of it and from the processors that run on top of it. And the trusted execution environments, such as those enforced by Intel or ARM processors, need to be isolated from the rest of the system, and so on. We've already seen that some systems do not have multiple non-trusting security domains at all. For instance, simple embedded devices have only a single security domain. In this presentation, however, and indeed in this knowledge area, we focus mostly on systems that do have multiple non-trusting security domains. Also, we mostly take an OS perspective. That means that we're going to talk about and introduce things from the operating system's point of view, rather than making an explicit distinction all the time between operating systems and virtualization. We're just going to introduce them from the operating system's perspective and only talk about virtualization when it's really needed, when the issues are different, because most of the times the issues are exactly the same.
And these operating systems, or these lowest levels of the software stack, are important because they manage the system resources in what is hopefully a safe and secure way. And the resources that I'm talking about are things like, the CPU, how much CPU time are you getting, how much CPU time am I getting, the memory of the system, the network bandwidth, maybe the disk, the file system, partition particular areas of the disk for particular users, and so on. However, it's important to emphasize that this in modern days is perhaps no longer enough. Right? This is the traditional resources, but in modern days, attackers have found ways to exploit much lower level resources for attacking a system. Okay? For instance, micro-architectural features, things that are below the interface that you as a programmer, even a programmer that programs in assembly, would see. So as a programmer, you may be aware of the architectural features of a system, the registers and maybe the instructions that are available. But there's a lot of other features that you don't necessarily have direct access to, micro-architectural features. And then we're talking, for instance, about translation look-aside buffers that are used in the address translation systems, caches, the memory management unit itself, maybe speculative execution engines inside the processor. And all of this are now being used by attackers to compromise the system. And if we want to build a system that is secure in the presence of attackers that do this, we have to manage these resources also. So this is important that we realize that the resources that we've been used to worrying about in the context of operating systems are perhaps no longer the only resources that we should be worrying about. Like I said, the operating systems and hypervisors are they form the lowest level of the software stack, and they form the bedrock on which all other security solutions are built. The operating system is different, or the lowest level of the software stack is different from the other levels, and we'll see that this is actually something that evolved in the early days of the dawn of operating systems. But nowadays, the operating system is able to execute instructions that cannot be executed by normal user programs. Okay, so privileged instructions, and the operating systems typically authenticate users or processes so that they can deny or allow them to do certain things. Okay? And to do that, the operating systems offer certain certain primitives to isolate security domains or users. Okay? Now, these are the sort of the core components on which further security can be built, and the application is responsible for enforcing the security beyond this point. Okay, the operating systems simply provide the means to do that, right? So that you guarantee that only processes with the appropriate authorization are able to access specific resources.
At this point, it's good to make a distinction between two important aspects of operating system security. On the one hand, there is the security that is offered by the operating system. So this is the operating system trying to make sure that your process can only access its resources, its files, its data, and not my resources, my files, my data, or indeed my CPU time. On the other hand, we have the security of the operating system, where we try to protect the operating systems against, intruders from the outside, perhaps malicious processes, perhaps, data arriving from the network or from malicious devices. Here we try to make sure that the operating systems cannot get compromised. Okay, so there's defense mechanisms that make sure that this is at least made as difficult as possible. And this is extremely important because once an attacker compromises the operating system, everything else is available to it because it's the lowest level in the software stack. Okay, operating system, and if there's a hypervisor, the same thing applies to the hypervisor. Once the attacker is able to control the operating system or the hypervisor, it has access to everything that runs on top of it. And that brings us seamlessly to the threats. What are these threats that the operating system should guard against? And these threats consist of attackers that are interested in violating the fundamental security properties that the operating system tries to safeguard. For instance, they may want to leak confidential data, they might want to modify data, and they may want to limit the availability of the system or its services, right? So these are the three main properties that we try to protect as an operating system: confidentiality, integrity, and availability. Okay, and these attackers, these threats, may come from different directions. It may be the processes running on top of the operating system, or indeed the operating system running on top of the hypervisor. Or it may be data coming from some remote site, perhaps network packets sent from the other side of the internet, trying to exploit your systems. Or it may be devices that are connected to your system, malicious devices, malicious hardware trying to exploit your system. Okay, and in some scenarios, we even include the operating system or the hypervisor itself in our untrusted code base, right? So, for instance, if we're talking about a cloud environment where we run, important stuff, secret stuff on hardware and a hypervisor, or perhaps an operating system that is not our own, right? And this is the most sensitive part of our intellectual property. We may not trust the operating system or the hypervisor that is provided by a cloud environment. So we have an additional environment that is even more secure than the operating system or hypervisor.
There are many types of threats that we know of, and the simplest kinds of threats against the operating system security are malicious extensions, where attackers manage to get the system administrator to load some malicious driver or some malicious kernel module because maybe it looks like it's doing something useful, but really it's a malicious thing. Okay. Then there are bootkits, where this could be a malicious extension trying to compromise the boot process. And because of this, it allows the attackers to gain control over the system even before the operating system is run. So this will give them a secure and very carefully hidden way to gain control, because after they have control, they can make sure that whatever you do on top of the operating system will no longer detect or prevent the bootkit, the malicious code from executing. But besides, these ways of compromising the system by means of Trojans or malicious extensions, we frequently see that they're simply compromises of the software by the use of software errors, memory errors, for instance. There are different types of memory errors that are either caused by software bugs, such as buffer overflows, but it could also be caused by hardware vulnerabilities, such as the rowhammer vulnerability in memory chips. Besides these bugs that corrupt memory, we also have bugs that allow you to leak data that you shouldn't be leaking. There are vulnerabilities due to concurrency. There are complex or not so complex side channel vulnerabilities where you actually indirectly obtain sensitive information. There are attacks that try to use up your resources and therefore make the availability of the system a problem. For instance, hogging the memory, CPU, buses, and so on. And there are bugs that cause deadlocks or hangs. They also jeopardize the availability of the system. So there's and this is probably not even a comprehensive list, but it gives you an idea of the enormous breadth of attacks that we have to defend.
So what is the role of the operating system or hypervisor in providing security?
At the highest level, as we mentioned, the operating system needs to manage the resources and provide confidentiality, integrity, and availability to the application. Okay. To do this, we have to provide isolation of the security domains that are relevant. For instance, the isolation of the different processes, and make sure that every operation that these security domains attempt to perform, make sure that they are mediated, right? So that there's some entity actually checking these to see whether or not it's allowed. Okay. And that's a very basic concept and a very basic way of approaching the security of a system. But some systems go much further than that and try to regulate even the flow of information, such that someone who has very little authority should not be able to read the data of someone with much more authority.
It is useful to distinguish between data plane and control plane operations, where control plane and data plane are defined somewhat analogously to how we define them in networking. Remember, in networking, we have operations that happen all the time, right? Whenever a packet arrives at the network switch and it needs to be, switched to some output port, this is a data plane operation. But there are also control plane operations where we configure the switch to operate in a certain way. Configure that some packets with a certain destination go to that output port rather than that output port. And when we configure the switch to provide isolation between two network segments and so on, those are all control plane operations. Well, analogously, we have control plane and data plane operations in operating systems. When, for instance, an operating system tries to protect a certain chunk of memory of one process from all other processes by configuring the memory management unit, the MMU. Okay. This configuration happens only once, and afterwards the hardware will simply check that all the accesses are not violating the security policies. Okay, so this is a control plane operation. In some cases, for instance, when the operating system operates on the system call arguments, the control plane and data plane are both active. Now, not clearly separating these two planes may lead to vulnerabilities. And here's an example where an operating system may use that memory that it made available to one process, to one security domain first, where all of it was properly configured using the MMU to safeguard all the accesses. It uses that memory, reuses that memory for another security domain, for another process perhaps. Okay, there we have the MMU that needs to be configured to disallow certain accesses, but we also have the requirement for initializing the data. You don't want to just blindly reuse the memory pages that were available to one process in another process, because then you would leak information. Okay? So this is a lack of clear separation between these data and control planes. Moreover, we shall see that the design of the operating system itself has strong security implications. And we're going to talk mostly about these operating systems where there are multiple security domains. So not the earliest systems where there's only a single security domain, or embedded devices where you only have a single security domain. We're mostly talking about operating systems with multiple security domains. And we shall see that we can structure that operating system in multiple different ways. For instance, we can have everything structured, organized as a single monolithic blob, or we can partition every part of the operating system as a separate component isolated from the others. And there are some variations of this. And these choices have a strong implication on the security of these systems. And what we're going to do is we're going to introduce these alternatives and then talk about these security implications. So what I've tried to do is sketch the different options for our design on a single slide with just 4 small diagrams. On the diagram on the left, we see the operating system as we had it in the earliest systems and still have it in embedded devices, where there is no separate security domain. There's just a single security domain and everything runs in it. The application, but also a scheduler, process manager, a memory manager, file system, network capabilities, whatever you need for this particular application to run. Okay, there's no separation, no isolation. In the second picture, B, we see that the applications themselves have been separated from each other. They've been isolated from each other, and also have been isolated from the kernel. So the kernel is isolated from the applications, and the applications are isolated from each other. But the operating system itself, right? So underneath the application layer, we see that the operating system itself is still a monolithic blob. So it contains everything: the file system, the device drivers, the network stack, the process manager, memory manager, scheduler. It's all a single blob of code. And it means that if there's a crash in any of these components, right, if there's a bug in any of these components and it causes that component to crash, it will crash the entire system. In the third picture, C, we see that the operating system itself has been partitioned, right? So in separate components. So the file system is separate from the network stack, the process manager separate from the memory manager. All of the drivers are separate and isolated from each other. And everything runs on top of a really thin microkernel. And the microkernel is only responsible for partitioning, some of the lowest level resources. For instance, it does some scheduling and it provides memory. Okay, so here, if there's a bug in any of the components, for instance, in the network stack, it will not take down the file system. Okay, so if there's a driver, a printer driver, say, that has a bug which causes it to crash, it will crash only the printer driver, and it may cause your printing process to behave funny, or maybe the paper that comes out doesn't contain the information you expected it to contain, but your system itself remains up. In the picture on the right, we see another system where there's only a very thin kernel, right? So a very thin microkernel, exokernel. And on top of that, we have 3 different boxes with applications. So in this case, there's very little functionality in the kernel also, just like in the previous model. But now all of the operating system functionality has been incorporated in the applications themselves in the form of libraries. So each of these applications is separated from the other applications and has just enough operating system support for its needs. So if it doesn't need networking, the library operating system that it runs against doesn't have to have networking functionality either. So it's just the bare minimum that is needed for this particular application. Okay, we call this a library OS. And this is a model that has become, more popular in recent years in the area of what are known as unikernels, which try to do this typically on top of a virtualization layer, a hypervisor, where we have these, dedicated virtual machines that run just a single application, and that application links against some library operating system. So what is relevant here is that within this application, the library operating system and the application need not be separated at all. So there's no different isolation, different rings of protection between the application and the library operating system, because the library operating system is really sort of part of the application. Okay, so these are 4 different models of operating system design.
Now, each design choice has its own security implications. Clearly, if we run everything in a single security domain, there is no isolation. This is not a system that is built for securing multiple security domains. In design B, we see that there is some security isolation. So the kernel is separate from all the processes, and all the processes are separate from all the other processes. But the operating system itself is still a single monolithic blob, and that means that even a single vulnerability there, right? So one security bug in the operating system may compromise all of the security of the, not just the operating system, but every single application also. Okay. The advantage of this this organization, by the way, which is the organization that we see, for instance, in Linux and Windows, is that if we do if there is an interaction between either the file system and either the process manager or the memory manager, this is a very efficient operation because everything runs in the same address space and every functionality is just a single function call. In the organization, the design that we see in the figure at C, it's a multi-server microkernel. We have actually partitioned all of the operating system itself in small components, right? So that means that there's much better isolation. A bug in your, I don't know, your printer driver, right? If there's a vulnerability in your printer driver, it will not, crash the entire system. It will not allow an attacker, if they're compromising the printer driver, to take over the full operating system and so on. So there's much better isolation. But the downside of this is that it's a slower design, or at least traditionally this has been the argument, because rather than function calls, now you have to make IPC calls to do to use the functionality of another component, right? IPC, inter-process communication, is much more expensive than just a function call. Moreover, it has some of the complexity of a distributed system. It's not really as bad as an actual distributed systems with, and everybody who build distributed systems can tell you, that building a distributed system is very complicated. It's not quite as bad as that, because unlike in a real distributed systems, all the communication here is local. So you don't go across the network, and that means that the communication can be assumed to be reliable, unlike in the wider internet. Okay. Finally, in the picture on the right, we see that we have these library operating system applications, and this is also what is currently being used in so-called unikernels, where we have a minimal system to support a single application. Okay, and each of the applications may run on, I don't know, a hypervisor or so, as a single small kernel, but it's only a single application and supports very limited functionality. It means that if there's one bug, one vulnerability in, I don't know, the application or the library operating system that is linked to that application, it means that application is toast, right? There's nothing you can do about that, but it will not necessarily affect the other applications that run on the system. Now, these are the kind of operating systems that we find on what I would refer to as general purpose systems. Okay, at least the last three, the monolithic one, the multi-server microkernel one, and the unikernel library OS one. But this is not always what is used in practice. For instance, in the Internet of Things, you often have devices that have very limited resources and do not support some of the hardware that is common in general purpose operating systems, such as, I don't know, malicious management, memory management units, or similar things. So they use operating systems that are very small, and one example of such an operating system is Riot, which can be just a handful of kilobytes long, runs on a vast variety of different systems, including 8-bit microcontrollers, but also, for instance, 32-bit actual processors, and do not necessarily require advanced features such as memory management units.
So the right way to design an operating system, the way you structure it, has been an ongoing debate for many decades now. And much of this started with a flame war between Andy Tannenbaum and Linus Torvalds. So Andy Tannenbaum was the author of the Minix operating system that actually inspired Linus Torvalds to write Linux. Okay, and one day in the early 90s, Linus Torvalds posted a message on the CompOS Minix newsgroup where he announced that, you guys, I've written a small kernel. It's not going to be anything big. It's specific to the Intel 386 processor, and I'm looking for help. And because the system was 386 specific and also monolithic, this prompted Andy Tannenbaum to respond to this. And he said, look, you shouldn't make your system specific to a particular processor architecture. The AT386 is not going to be around forever. You've made your system non-portable. Moreover, you've designed your operating system as a monolithic kernel, and this is really less reliable than if you were to compartmentalize this. Ergo, I think Linux is already obsolete. And this, prompted an angry response from Linus, where he said, I think Linux is more portable than Minix. And he actually gave some sophisticated arguments, and the arguments were, rebutted by the other side. And this went on for quite some time. This debate raged on through the decades, and it had many manifestations and many variations. For instance, some people on the Minix side argued that compartmentalization gives you much better reliability than a monolithic system, where a single bug in your code, a single vulnerability, means that a crash will, kill your entire system. And the other side would argue that, if you have something like a microkernel, a multi-server microkernel design, such as the one that Andy Tannenbaum advocated, what you have is kind of a distributed system, and everybody knows how difficult it is to get a distributed system correct. Okay. On the other hand, if you have a monolithic system such as Linux, everything is simpler because it's now just function calls. Everything is just a function call away. Now, there are some things to be said about this. It's really, when you think about it, it's a distributed system only in the sense that there are multiple components, for instance, but it's not having the same properties as an actual distributed system. For instance, you don't lose data across a network, so there's no lossy connections. But anyway, so both sides had very sophisticated arguments. And what is interesting is that it's unclear who won, right? So there's no way in which we can argue that Linux is obsolete in any way, right? It's extremely popular. It's one of the most popular operating systems in the world. For instance, Linux itself runs on many servers in the cloud and elsewhere. It's basically the basis for Android. Super dominant in the mobile and server market, and now it's even incorporated in Windows. So Linux has done quite well for itself. Thank you very much. On the other hand, surprisingly, perhaps to many, Minix also did really well because it was incorporated by Intel in its processors. So from, I think, 2011 onwards, Intel started adding a separate processor to every x86 processor, and it was known as the management engine. The management engine was a separate, highly privileged processor, could do all sorts of things. And on this highly specialized environment, it ran an operating system that was derived from Minix. Okay. So both systems have been extremely widely deployed. Moreover, some of the ideas of, say, the multi-server operating system that Andy Tannenbaum advocated have been incorporated in other operating systems, including Linux in some cases.
What about virtualization? Well, if you look at it, virtual machines are essentially just another security domain. Okay, so that means that you have to provide isolation and security there. And if you want to be extreme about this, since this looks pretty much like processes that also need to be isolated, well, maybe you can use these virtual machines to partition an operating system, which is exactly what happened in some solutions, such as CubeOS. Okay. And then you get something that is not unlike a multi-server operating system. It's been argued that microkernels are very similar to hypervisors. There's been a paper by Steve Hand who argued that perhaps hypervisors might be microkernels done right. Now, this created a response from the microkernel community who disagreed, but they are somewhat similar. So there's that. So microkernels versus hypervisors. There's also another issue where there's a lot of debate about which is the best solution, and that is virtual machines or containers. So virtual machines are truly separated typically by hardware mechanisms nowadays, whereas containers offer somewhat similar functionality, but the isolation is much less hard. So you have, for instance, a way to partition resources somewhat in I don't know, Linux, and this is known as containers. So the containers are isolated as well as possible with their own kernel namespaces. They have separate resource limits, etc. But in the end, they share the same underlying operating system kernel. Often they share binaries and libraries and so on. So on the one hand, this makes containers more lightweight. On the other hand, it also means that they have slightly less separation, strict separation than. So because of this, and if we ignore the issue of management, virtual machines are typically perceived as slightly more secure than containers. Because they have more strict partition, they share a very, very thin hypervisor rather than an enormous blob of monolithic operating system. But on the other hand, you may also argue that containers have some properties that may make them more secure than virtual machines also. They are super lightweight, for instance, and since they're so lightweight, we can actually partition applications into really small services running in containers, separate containers, which provides more isolation inside the application. Moreover, if you have only a single system to worry about, right? So maybe a Linux operating system and all the containers are running Linux also. It also reduces the attack surface. You don't no longer have multiple virtual machines with multiple operating systems that can be attacked. And perhaps even it's more secure because the management is simpler. You only have to worry about one particular code base that you need to keep up to date.
Because security is so important in operating systems and virtualization solutions, because they are, after all, the lowest levels in the software stack, and any compromise here will have repercussions for everything that runs on top of them. Because of this importance, security in operating systems and hypervisors has often been discussed in fairly fundamental terms. So people have thought about security principles. What does it take to build a secure operating system? And very formalized models of how they should allow access to certain resources and disallow access to others. And we're going to talk about these principles and models next. So, like I said, the operating system and virtualization layer are the foundation, the bedrock on which we build all higher level security. And the principles and models that we discuss are used in different ways. So the security principles serve, for instance, as a set of guidelines, how to design our system in a secure manner. So here we have a set of security principles. How do we build a system that adheres to these security principles? They also serve, for instance, as a checklist. If we have an existing system, how well do they adhere to these security principles? Now, the models that we talked about, so the access model, that how we control the access to information in our system, they guarantee certain properties, right? So the flow of information should adhere to certain properties, such that we cannot leak confidential data to people who should not be allowed to access them.
And the best known set of security principles are probably the principles by Salzer and Schroeder from the 1970s already. And the principles are things like economy of mechanism, fail-safe defaults, complete mediation, open design, separation of privilege, least privilege, least common mechanism, and psychological acceptability. Now, all of them are important. We can't discuss all of them in great detail. But just to give you an idea, least privilege, or least authority, sometimes known as POLA, the principle of least authority, indicates that your software component, each software component, should have the rights, the privileges to do what it needs to do, and no more. It should only have those rights, okay? Because if they have more and they get compromised, it actually makes the security problem bigger. The principle of least authority is a very important security principle. Now, all of these principles are fairly generally accepted. Open design may be the exception, right? So there's a bit of a debate about that, and I'll talk about that in a minute. Now, other design principles have been added to this, and most of them have some merit to them. And I'm just going to mention two. One of them is the principle of minimizing trusted code, so have a trusted computing base that is as small as possible. And the second one is the principle of intentional use. So these two principles have been added to the set of security principles that we talked about so far. So where the principle of intentional use means that we authorize only that what is really intended. So this is what you really need for this particular action, not just what is convenient or expedient or something that's overly broad. And we can apply these principles, for instance, Salzer and Schroeder, to the different designs. And if we have the design on the left, we know that the trusted computing base comprises everything, all the software. All mechanisms are common. There's no fail-safe defaults. There's no mediations, and no principle of least authority. Whereas in design number B, we have separation between the applications and the kernel, and so that's already a little bit better. There's some mediation, for instance, for all the operations performed by the applications, but the operating system itself is still a single security domain. So as far as the operating system is concerned, there's very little privilege separation. There's no principle of least authority, and so on. In contrast, in the multi-server microkernel organization, there's a very fine-grained decomposition, which allows mediation at all the boundaries. There's much more opportunity for applying the principle of least authority. You can have fail-safe defaults. The trusted computing base can be as small as it needs to be, and so on. And the system on the right, we see that there's for each application there's still a single domain, but the trusted computing base can still be fairly small, because we only provide the operating system support that is needed for that particular application and cut out all the rest of it. The economy of mechanism is quite good. There's not much that is there. The least common mechanism is adhered to. There's only very little that is shared between the system. Mediation is beyond the applications. It's well adhered to, and so on. What about this one principle that we briefly mentioned? So the principle of open design. It's sometimes referred to as Linus's law by Eric Raymond. So it was named in honor of Linus Torvalds. And the idea is that if we make all of our software open source and available, there will be more people looking at this the code, and the probability of there remaining bugs in the code will be smaller because of that. Because given enough eyeballs, all bugs are shallow. And there's something to be said for this. This is not, complete rubbish. But it's also important to have at least a footnote there to indicate that, sometimes we still find bugs that are, tens of years old, even in security critical programs such as the Linux kernel or products such as OpenSSL. So it's not always the case that if you simply have enough eyeballs looking at code that you will find the bugs more easily. Now, besides the principles that help guide or check the designs, we also have access models that give us rules about how, for instance, how information may flow through a system. The access to data, what should be allowed in terms of accesses to data. And in the strictest model, we can try to guide and regulate the actual flow of information. Now, there are different types of access control models. We have mandatory access control, discretionary access control, that should be a D, and role-based access control.
So mandatory access control is a system-wide policy which determines, which resources, which documents and information you're allowed to access. And even though you have access to a certain, piece of information, doesn't mean that you can give this to just arbitrary users on the system. You cannot share this information necessarily, within the system at least, with people who have less clearance than you do. Okay, so it's a mandatory access. Contrast this with discretionary access control, where if you have access to a certain object, you can also have some say over who else can get access to that object. So you may transfer some of your rights to other users. Okay, and that, if you do this in as the only mechanism, it's very hard to control this flow of information, right? So because once you have access, you can share it with everybody else. So discretionary access control makes the structured control of the flow of information much more difficult. However, you may also have a hybrid system where you have discretionary access control within the boundaries of mandatory access control. So even though the mandatory access control decides, the strict boundaries, within those boundaries, you can, share in ways that you see fit. You have discretion to share some of the information with others, as long as you don't violate the boundaries of mandatory access control.
Let's have a look at the principal mandatory access control models. And the two well-known mandatory access control models that we're going to discuss are Bell-LaPadula and the BIBA model. So Bell-LaPadula is a security access control model that focuses purely on confidentiality. Okay? It was the designed for the US government, so the Department of Defense was interested in this because they wanted to have, their mainframe computers usable by multiple users, and some of them would have different clearance levels, and that means you need some multi-level security. So you want to make sure that the top secret data cannot leak to people who only have access to a clearance for I don't know, confidential or just classified data. And the model determines that a principal that has medium clearance cannot read any data that is produced by a principal at a level higher. So, for instance, if you have clearance for secret data, you cannot read any data provided by a principal with top secret clearance. And you can also not leak data, you cannot write data to anything that is below you in terms of clearance. So you cannot write down. So you can access objects with a top secret label, and you cannot write to any documents with only a classified label if you have a security clearance level of secret. BIBA is concerned with exactly the opposite. So confidentiality is not the only problem. There's also this issue of integrity. You don't want someone at a lower rank to edit the data, the information, for someone at a much higher rank. Okay, so BIBA gives exactly the opposite rules of Bell-LaPadula. So here we can read up, but we cannot write up. And we can write down, but we cannot read up. Okay, so that's a different model. Both of them are so-called lattice models. So you actually provide an ordering in confidentiality levels. Okay, so there's classified confidentiality, confidential and secret, and top secret, for instance. And these are partial orders. So that's how you regulate the flow. Then for completeness sake, we mentioned there's also role-based access control, where we restrict the access to objects on the basis of roles which a process or user may play. For instance, you may act in the role of a manager of a department, or maybe just a regular employee, or the CEO, and on the basis of that, you have different accesses. Okay? If you do this carefully, you can implement both discretionary access control and mandatory access control policies using role-based access control.
So like I said, with discretionary access control, the users have control over the access. And a good example of discretionary access control are the file permissions in Unix. So in the example, we show the contents of a directory, the TMP directory. And we see that there are 3 documents there: mydoc, hello world, and id rsa.pub. And this user, Herbert B, has read rights and execute rights on the hello world document, right? So we can see this in the on the far left of the line for hello world. It has RWX for the owner of the file. So the owner has read R, W write, and X execute rights on this this file. The people in this group, that's the next 3 characters, only have read R and execute permission, and they don't have the write permission. And all the others do not have any access at all. Okay, so that's how permissions work in Unix. But it's discretionary. So if Herbert wants, he can transfer some of his rights to others. For instance, he can do a chmod, change mod, to make the hello world file readable and executable to others, so that it's read, write, execute for himself, read and execute for group, and read and execute for others. Now that we've seen the principles and the models for control of the information flow in our system, the access models, now it's time to look at the primitives that are needed to provide isolation and mediation in our operating systems and hypervisors. And that's what we're going to look at next. And before we begin, I want to emphasize that this is not new either. In fact, it was very much part of Multics, the first major operating system that was designed with security in mind from the outset. And we find that in Multics, the principles and the access models for information flow control, such as Bell-LaPadula, are deeply ingrained. And this should not surprise anyone if you know that Jerome Saltzer, who came up with the Saltzer-Schroeder security principles, was one of the lead engineers on the Multics team. And so Multics had many security innovations that are still found in today's operating systems. In all modern popular operating systems, we have some remnants of Multics, even though Multics itself is dead and never became very successful in terms of usage. Many of its inventions are in all of the operating systems that we use on a day-to-day basis. So Multics, for instance, introduced these rings of protection so that you have your operating system or your hypervisor running at a ring of more privilege than your user processes. It introduced a hierarchical file system with support for discretionary and mandatory access control, and where the mandatory access control was a direct implementation of Bell-LaPadula. And moreover, Multics was constructed out of many small software components that were all strongly encapsulated, isolated, right, and accessible, mutually accessible only via these published interfaces where all the mediation took place, adhering to the security principles that I alluded to earlier, the Saltzer and Schroeder security principles. Okay, and again, since Multics did this first, and although Multics was not very successful, all of these principles and all of these ideas are now found in all of our modern operating systems. So the Multics operating system became very influential in another way also. It was a main ingredient for what is now known as the famous Orange Book, or the Department of Defense's trusted computer system evaluation criteria, which describes all the requirements for evaluating the security of a computer system. And this is strongly based on Multics. And as mentioned, Multics was extremely advanced. And you could argue that perhaps it was too advanced. So it has a lot of security mechanism primitives and principles that it adheres to. But because of all of this, it also became incredibly unwieldy. And it caused, some of the developers, in particular Ken Thompson and Dennis Ritchie, to step out of this project and start their own new operating systems, which they called Unix, as a pun on Multics, right? And that name stuck, although it was spelled a little differently later. And like all operating systems, it relies on a small number of primitives to provide security.
So the primitives that we require for this isolation and mediation are manifold. So we must be able to authenticate users. Otherwise, how can we determine whether or not you should have access? We have to support access control. So there has to be a mechanism, a primitive for doing this. We have to have protection of memory. So we should not allow one application, one security domain to access the memory of another security domain. And we need to be able to have these rings. So there should be some code that runs at a higher privilege than other code. Okay, so that the privileged code can configure the isolation and mediation as you want, but the non-privileged code cannot change that. So authentication, we're not going to say too much about this. There are many ways in which we can do authentication. Usernames and passwords are a common way of authenticating yourself to an operating system, but you can also have smart cards or biometrics such as fingerprints or retina scans and so on. If we have multiple factors used in the authentication, it becomes much harder to bypass it. So if we have something that we have such as a smart card, something that we know, such as a password, and something that we are, such as our retina scan or our fingerprint, it becomes more difficult for the attacker to obtain all of those factors and bypass the authentication check. Okay. However we authenticate ourselves, the operating system will then maintain some identifier for each user, okay, and also a process identifier for each process that runs on behalf of the user. And in the running of these processes, it will track the ownership and access rights. All of these require certain credentials, and the credentials need to be stored in a secure place. So nowadays, with modern solution, we may use a virtual machine or maybe some trusted platform module to ensure that the credential store where these credentials are stored is cryptographically sealed.
Next primitive after authentication is access control. And besides the access control models that we've seen, such as Bell-LaPadula and Viva, we have access control primitives. And there are multiple options here. What most operating systems use these days, at least, is access control lists or some variant of an access control list, which was already in the Multics file system. So what we do is we basically, at least in Multics, what we had was an access control list for every block of data in the system. And the access control list simply is a table that specifies for each of these data blocks which users can do what sort of operations, what access rights they have. Most modern operating systems have also adopted such access control lists. For instance, in Linux, we have these permissions that we can see if we look at the access control list for a particular file using the get FACL, so the file access control list. And in this particular example, we see that I'm asking for the access control list for a file called my script. It tells me all the information about the file script, and it also tells me, what the accesses are, the privileges are for users, for the group, and also for others. But it seems like this is just the old Unix file permissions. But it turns out that you can actually build more extensive access control lists. Okay? But access control lists are essentially just that, tables where we specify for particular objects what operations particular users may perform. So what about mandatory access control today? Well, nowadays, most of the larger operating systems, such as Windows, BSD, Linux, all support some form of a mandatory access control. So, for instance, for Linux, we have ASCII Linux, which is a secure set of security patches, which was made originally by the NSA, and it gives both resources and users or processes a context, and the context consists of three things: a username, a role, and a domain. And what you can define is system-wide policies for access control on the basis of these contacts. For instance, which contacts processes must have to access certain resources with specific operations, so in specific ways. Okay, and I think the name already indicates of the context components, username, role, and domain, that role-based access control is indeed possible, as is mandatory access control. Now, access control lists are not the only option for regulating the access to systems. The other main model, which is also quite old, also from 1966, besides access control list, is capability. So an access control list has information, a table with information about it, whether a particular process P can perform operation O on some resource R. In contrast, capabilities do not require such a table, such administration, because they embed each capabilities like a key, and it embeds these permissions in the capability itself. So the capability proves that the requested access is permitted. Okay, and we even in traditional operating systems that and the basics of operating systems that we get used to in universities, we have some notion of a capability, or at least something that is very similar to a capability when we talk about, for instance, file descriptors. If you have a file descriptor, it means that you can perform operations on that file, right? So the file was opened, you get a file descriptor, and that means that you can perform some operations on this. So like that, a capability is kind of like that, a token, an identifier, a key that gives the possessor of the capability the rights to access an entity or an object in the computer system in a certain way. So the access rights are contained in the capability. So because the access rights are embedded in the capability, of course, it must be impossible for third parties, external parties, to forge these capabilities. So either you have to do this in some trusted environment and keep the capabilities there. For instance, you keep the capabilities in the kernel, say, or you have to protect the capabilities in another way. For instance, the Amoeba operating systems had the capabilities protected in a cryptographic way. And either way, you could not forge the capabilities. Okay? But the capabilities are pretty much like digital keys, and you can just pass them on to other entities, right? So you can actually pass the capability or a subset of the access rights that the capability gives you to another process. Okay, and there is, of course, a problem there, or a possible problem there, that perhaps you don't want the capabilities to spread arbitrarily and without any way of controlling this. So a common solution is to add some flags to the capabilities that indicate whether or not the possessor of that capability is allowed to copy the capability. Okay. So that is how you can control the spread of the indiscriminate spread of. If we compare access control lists with capabilities, there are many advantages and disadvantages to both. But the access control list seems to be a little bit less flexible. So the access control list is based on users, right? So the user with some identifier can do, some operation, whereas a capability can be much more fine-grained. So you have perhaps a separate capability for sending and receiving data. Okay, an access control list is because it's so centered on the users. What typically happens is that whenever you have a process, the process runs with the full power of the user, right? So that means that everything that the user can do, that process can also do. And that, of course, is not necessarily adhering to the principle of least authority, because now you can do much more than you perhaps strictly need to be able to do. So the capability is much more fine-grained, and you just give a process the capability that it requires, or a number of capabilities that it requires, and that is much better for adhering to the principle of least authority. Okay. And finally, if you have a lot of users, a lot of resources, you might actually get very large access control lists. Okay. So all of this indicates that perhaps capabilities are superior to access control lists, but it's a little hard to argue that in the general case, because there are also disadvantages to capabilities. And one of the largest disadvantages is revocation. So with an access control list, it's really easy to revoke access right, because you just look at the table and remove the access right for a particular user, say. With a capability, it's much more complicated, right? So your capability has been given out, and maybe it's been replicated, so it may have spread to many places. And now you want to revoke the capability, or what's worse, you may want to revoke the capability for only a subset of the processes. Okay, that is much more complicated. Over the course of history, many systems with support for capabilities have been built. Some of these systems had capability support built in the hardware. And this all started in the dawn of computing with the MIT PDP-1 time-sharing system. Okay, and it has had a number of notable other computers with hardware support for capabilities. The Cambridge TAP computer depicted here on the slide is one of them, one of the more famous ones. But even today, we have systems that initially researchers built with support for capabilities, such as the very interesting Cherry project, which has capability support built in hardware and which has now received funding to actually do this seriously and produce actual hardware out of this. So capabilities in hardware are still very much alive. The same is true for capabilities in software. So we've had numerous operating systems with capability support in software, and an interesting one, I thought at least, was the Amoeba operating system, where you don't rely on hardware or indeed the kernel or some privileged security domain to handle your capabilities. Rather, you seal the capabilities cryptographically, which means that even if you handle them in user space, which is what we do, the users cannot tamper with the capabilities or forge them or whatever. Okay, a more modern systems that use capabilities are the L4 and secure L4 microkernels, which have full-fledged support for capabilities. So SEL4 is the secure L4 system that was built originally by what was called NICTA, which is now called Data61 in Australia, and it's a formally verified microkernel with capability support. And another good example of capability in modern systems is the Capsicum project in FreeBSD, which offers capability support in the FreeBSD operating system. Okay, so capability support in software is also very much alive. Now, it's very common to hear people talk about capabilities in Linux also, but it's important to realize that these are not real capabilities, at least not capabilities in the sense that Dennis and Van Horn had in mind in 1966. They are much more limited and should not be confused with the real capabilities of the systems on the previous slide. Now, besides the access control that we provide in the operating systems, we also have to deal with the real world. And the real world might not use the operating system to access the resources at all. For instance, maybe you limit access to particular files on the file system via the operating system, but the data is still there on disk. Moreover, it may be that the file is deleted, but the data is still there. Perhaps the operating system only removed the metadata from the file system so that it can no longer access it via the file system, but the data, in terms of if it's a magnetic disk, in terms of magnetic traces, is still there on the physical disk. Okay, so it may even get worse, right? So maybe you're even overwriting the actual blocks with new data, so you really want to securely delete this. But then there are still some magnetic traces very close to the actual data tracks, and maybe there is still the information there. You may be able to read this still. Okay. Similar things happen in SSD, where it's not the operating system that decides physically what will be written and when, but it's the SSD itself. So the operating system has no control over this. So that means that deleting files securely is actually a difficult problem. And moreover, if you delete something, you have to be very careful in how you do the deletion, because maybe there's more copies than you care to think about because of backup processors, for instance. Okay. So if you want to secure the data against physical access, you have to clearly do a lot more work, right? And this goes beyond this knowledge area, but one particular powerful way to at least help in this sense is to simply do always encrypt your data. We've talked about authentication. We've talked about the access control. via access control list capabilities. There's one other really important primitive that we have to talk about, and that's a memory protection. So we want to prevent one security domain from accessing the memory of another domain if it's not privileged, if it's not allowed to do so. So what we can do, the simplest thing is to never have any data from one particular security domain in memory at all before we switch to another domain, which of course would be would be perhaps secure, but it would be very inefficient. Or we have to add memory protection. And memory protection has been around for a long time already, available in Multics. And what we do is we're going to give every process its own processor state, so its own set of registers that we're going to use for that that process, and its own subset of memory. So the registers, we actually do take care of the registers in the way that I described earlier, where we basically say whenever we switch a process, we save the processor's register state, so the state of the processor, and loads the processor state of the new process, and then we start running. And we also give every process its own subset of memory, and there we add memory protection. So we do a combination of the two solutions that are sketched above. Okay, and whenever we do a context switch from process 1 to process 2, we save the processor 1 state, load the processor 2 state, and then adjust the bookkeeping such that the access rights to memory that you shouldn't have access to are adjusted, and the memory areas that you should have access to are also adjusted. So how do we do this bookkeeping? Well, on today's general purpose computing systems, we use page tables for this. So the idea is as follows. The software wants to access a location in memory, and it uses a so-called virtual address for this. And the virtual address, in this particular case, we have a virtual address of 4 times 9 plus 12, 48 bits. Okay, and it's chopped up in 5 different pieces. So the last 12 bits are an offset in a page of 496 bytes. Okay, so this is an offset in that page, and that's where we find the byte that we want to access. Now, the other 4 chunks of 9 bits represent offsets in so-called page tables. So we have a top-level page table, or a page directory. We don't want to care about the terminology too much in this lecture, but we have a top-level page table that is pointed to by a register in the processor. We see this on the left. Okay, and the first 9 bits of our virtual address form an offset into this page table, which is also a single page of memory. So it's 496 bytes containing addresses, physical addresses of the next level page tables. So an offset into this first level page table, the top level page table, and we find it contains the number 3. So we look at 0, 1, 2, 3, the 4th entry on this page table. There we find the physical address of the next page table that we need to use. Okay, and that is indexed by the next 9 bits, which in this particular case contains the value 2. So we now look at 0, 1, 2, the 3rd entry in that page table, which contains the physical address of the next level page table, where we again index with the bits that we find there, which is the number 7. So it's the 8th entry in this page table, and there we find again the physical address of the last level page table. So this is the lowest level page table, and here we index with the remaining 9 bits. In this particular case, it contains the number 6. So we look at entry, the 7th entry in this page table, and there we find the physical address to the actual memory page that contains the data. Okay, and like I said, we use the remaining 12 bits to find the byte that we want to access on this page. So we have virtual addresses that get translated to physical addresses. Okay, And it's important to realize that the page tables have entries containing, the physical addresses. Each page table entry is a physical address of the next page table, and eventually it's the address of the memory page, the physical memory page that contains the data. And of each page table entry of 64 bits, a number of bits are unused. So there's a physical address that is there, which points to a page. So that means that there are 12 bits not used. Okay, and one of those bits is the supervisor bit, and that determines whether or not you're allowed to access the page from user space, right? So if you're not a supervisor, or if you can only access this page from the kernel, say the highest privileged level. Okay, so that's how we can separate kernel pages from user space pages, even if we use the same page table structure. So it may be okay if the kernel pages are mapped into your process address space, because the process itself, so the user space code, cannot access the kernel pages anyway, right? Because they don't run with a supervisor privilege, so they cannot access those pages that are marked with the ASBIT set. It is important to realize that every process has its own virtual address space. And that means that, I cannot access your memory because your virtual address space will be mapping different, physical pages than mine, right? So even though we both may be accessing the same memory address, virtual memory address, say 1000, it will be mapped to, something different, some other physical page. Okay, and unless we explicitly share memory, I am not able to access your memory. Okay, so this gives us isolation in terms of memory. And like I said, we have the supervisor bit to separate kernel memory from user space memory. So it's fine if we keep the kernel memory mapped in the virtual address space of each process. Okay, so now we have a way to isolate processes in terms of memory. Every process has its own virtual memory address space. Okay, now paging is not the only solution for this. So the original Multics system used paging, but also had support for segmentation. Segmentation was also supported in the x86, so up to the 30-bit, up to and including the 32 bits x86 architecture. And what they supported, in fact, was both segmentation and paging. So you first did segmentation, and then you did paging. Now, I don't want to talk about segmentation because it's no longer supported in most of the popular processors today. In fact, even the x86 dropped most of the support for segmentation in the 64-bit version of its processor. So it's no longer the hip way of doing things, and it's no longer really there on x86, 64, although there are still some remains of the segmentation that we have there. Things like segment registers are still there, and some other things. Segmentation wasn't used very much, so the only desktop operating system that we had that used segmentation that became popular was the OS2 operating system, but that is now also dead. But the AS400 operating system was actually a popular system that used segmentation. Okay, so that's on the larger systems, and that of course became quite popular. Paging and indeed segmentation are not the only tricks that you can use to provide memory protection. And what we see in modern hardware is that there is an plethora of new techniques or new based on old ideas typically, but newish techniques to help protect memory from illegitimate accesses. And some of these techniques are successful, others are not so successful. An example of the latter is what is known as Intel MPX, so the memory protection extension that Intel added to its processors to prevent buffer boundary violations. Now, this was a complete failure and it was dropped eventually, but it gives you an idea of the tricks that hardware vendors are trying out to see if they can help improve memory protection, memory isolation better. Now, MPX failed, but then there were other ideas. For instance, memory protection keys. And it's important to realize that both memory protection extensions and also MPK, the memory protection keys, are based on old ideas, right? On these Intel processors that we have today, they basically help you partition your address space in 16 different regions. So what the MPK functionality allows you to do is to use some of the unused bits in your page table entries to indicate a key, right? So you basically say this page has a certain value, say 7, and so that means your page is red, and another page table entry is marked, with value 3, and maybe that's blue, right? So now you have two different types of pages in your address space. There's blue pages and red pages. Okay, so how does that help you? Well, there's another thing that you add. There's a 32-bit register that contains 2 bits for each of the keys. So for each of those colors, it indicates whether or not you can read and or write those pages. So if the register says that you can only read blue pages, but you can read and write the red pages, it means that this data access is now enforced. Okay, and of course the page table entries can only be modified by privileged code, so code running in your kernel, say. Okay. And that means that you, as a user space process, you cannot modify this. The only thing you can modify from user space code is the content of this register. So how does that help you? Well, it means that you can set the accesses that you want a certain chunk of code to have to certain pages, certain data, right? For instance, if you have cryptographic keys that you want to protect, maybe you only want to have access to those cryptographic keys, so the pages on which you store the cryptographic keys. Maybe you want to give that access only to cryptographic code that actually needs to access it, and make it inaccessible to all the other code in the system. So you change the register whenever you jump into the cryptographic code, and you actually change it back when you come back. Okay, that gives you a form of isolation within your process. Another way of providing strong protection with a hardware trick is known as memory tagging extensions. Again, this is based on an older idea, and SPARC, the SPARC processor, already had an implementation of something that was, basically memory tagging. And nowadays, we're also going to find this in ARM processors. ARM 8.5 has, I think, support for memory tagging. And here the idea is, again, really simple in and of itself. You give every chunk of memory a tag. Right? Every chunk of memory gets a 4-bit tag, say. Okay? Moreover, every pointer that you have in your system also gets a tag. And you don't store this separately. You actually store this in some, of the unused upper bits of the pointer. You don't actually use the full 64 bits of your pointer anyway. Architecturally, you only use maybe, say, 48 bits. So you can use the upper bits, at least 4 of those, to store the tag. Right? And now what you do is you make sure that a pointer and a memory that it dereferences, so a pointer that is dereferenced and a memory that it tries to access should match in the tags. Right? So here's the idea, right? If you have an array, a buffer, and you have a pointer into that buffer, they are given the same tag. And that means that every time you dereference the pointer, the hardware will check whether or not the tag is still the same. And that means that if you try to dereference a pointer to access some other memory, so this was a red tag, and now you're trying to dereference a pointer to access blue memory, so you change the value of the pointer, and now it points to blue memory, the colors don't match. And that means that there's a problem. And this is a memory error that may allow you to crash the program or so. So this will stop most of the attacks that target spatial and perhaps also temporal memory errors. And like I said earlier, not all processors offer such really advanced protection schemes at all. Right? For instance, devices in the IoT are often very simple, and they may not even have an actual MMU. It may not have a memory management unit. Although some of them offer a much simpler memory protection unit, which is not an MMU. It doesn't translate from virtual to physical addresses, for instance, but it does offer protection, right? So it may define different regions with different access permissions. And now, of course, there's the case that you may have even more threats. Maybe it doesn't stop with the malicious processes. It may be that you're also worried about, I don't know, your kernel being malicious. Okay? So even if your kernel is malicious, you still want to be able to execute some code without, the attacker being able to compromise it or to eavesdrop. So this is, for instance, what is done in trusted execution environments such as Intel SGX or ARM Trust Zone, or there's a bunch of others. Okay? And here in Intel's SGX, you basically run a trusted execution environment, which is an enclave. You can run part of your application in this enclave, and the hardware tries to protect this code from any interference, anything that the attacker could do from the operating system. So it cannot see any values that are in memory in the enclave. It cannot read the registers in the enclave, and so on. Okay. And the way it guarantees that, for instance, is by means of encryption. All the data that is stored in memory will always be encrypted, and it's only used in unencrypted form in the CPU itself. Okay. And ARM Trust Zone is a slightly different model, right? So in this case, there's also a trusted execution environment, but now it's what is known as a secure world, and the normal code runs in the normal world, and this is where you run your operating system, maybe Linux or Android or what have you. And in the secure world, you run another operating system. So there's also an operating system in the secure world, and there you run, trusted applications. Okay. So the secure world runs its own operating system. So that's different from SGX, where part of your application runs in this trusted execution environment. In the ARM Trust Zone model, you run, a separate app in your trusted execution environment. Okay, and then there are other threats that you may want to guard against also, right? It need not just be the operating system. It need not be other processes or packets arriving over the network. It could also be malicious DMA, right? So maybe there's a device attached to your USB-C connector, maybe your Thunderbolt plug, which directly interacts with the PCIe bus. And that allows the attacker to read and write to memory, and you want to prevent illegitimate accesses to memory pages, stuff that this device should not have access to. And one way to at least partially remedy this is what is known as an IOMMU, which is just another MMU, much like the MMU that we saw earlier, which is responsible for doing the page table walk and so on. But now the IOMMU protects against devices that are trying to access memory. Okay, so it's just like a regular MMU. It translates addresses that are used by the devices rather than addresses used by the processors that are translated to physical addresses. We now translate addresses used by the devices to real physical addresses. And it's doing that in roughly the same way. So it has page tables and it offers the equivalent protection, so page table based protection, so that your device can be limited to access only the pages, the physical pages that it should have access to, rather than having full access to everything. And there are many other hardware features that are either already in the in the processes that we use on a day-to-day basis, or are currently being worked on. So there's a lot more out there and a lot more to come. One particular hardware feature that we've had for a very long time already is the notion of protection rings, or rings of privilege, as they're sometimes referred to. They were introduced. This was one of the most innovative features of Multics. Introduced in the Multics system. You need hardware support to do this properly. And the idea here is that you have a hierarchy of privilege. So there's a code that runs at a higher privilege in the inner ring. So ring 0 has the highest privilege, can do certain operations that none of the other rings can do. If you have code there, this is the most privileged code. This is where the kernel of your operating system lives. And the layers above that have less privilege, are not allowed to do certain things that the inner rings are able to do. So your application runs, say, in ring 3, and the kernel of your operating system runs in ring 0. And whenever ring 3 applications or ring 3 code needs something that requires higher privileges, right? So maybe it needs more memory and the page tables need to be adjusted. What the code in ring 3 will have to do is call into ring 0 code and ask it to do this on its behalf. And the mediation takes place on the transfer from ring 3 to ring 0. So the ring 3 code will end up in very specific places in ring 0, where the ring 0 can, maybe by means of a system call, where ring 0 can actually validate the call. Are you even allowed to make this call? Are you allowed to use these arguments? Is this, if you want to adjust page tables, does it even work for you? Can you actually do this? So all of this is, extremely useful for the principle of full mediation. You want to have complete mediation. The calls are handled by the specific code in the most privileged ring. And sometimes we also have to do the opposite, right? So maybe we need to give some signal to the application layer from the ring 0 kernel code. So in that case, Unix for instance, uses the notion of signals, where you temporarily stop the code executing in ring 3. And instead deliver a signal. And if the ring 3 has a signal handler installed for this, this will be executed. And after the signal handler is executed, you basically go back, and the kernel will make sure that the process continues at exactly the same place where it was interrupted. The protection rings provide boundaries. So the interface between rings are an excellent place to check these system calls, to do the mediation. Now, what does that mean when we saw that already? What does that mean in the case of say, capability systems? Well, in a capability-based system, this is the right place where you can check the capability. Okay. It may also be a good place to check whether or not this ring 3 code, so this least privileged code that is trying to do something, is even allowed to make the call that it's trying to make. So some operating systems, such as the Minix 3 multi-server microkernel operating system, it will limit the number of calls, the set of calls
that you can make from your unprivileged code, right? So it will try to apply the principle of least authority and not give everybody all access to all the calls that can be made. Now, this sounds really good, and we had this ring 0 code containing the most privileged code, but the reality is that this model has been adopted, has been super successful, and so successful that why limit ourselves to just the handful of rings that we have there? Why not add a bunch of rings to it? So you could argue that hypervisors in a virtualization technology, if you have hardware-based virtualization, that hypervisors run at a ring below ring 0. So they are more privileged than the kernel of your operating system. So they run at ring -1. And then there's another management mode, another mode in which your CPU can operate in, say, Intel processors, which is called system management mode. And that is even more privileged than that. So we call that ring -2. And then there is even another mode, another processor within your Intel processors, right? So which runs its own little operating system based on Minix, okay, which is extremely privileged also, and sometimes this is referred to as ring -3. Although you could argue whether this is deserved. Anyway, so the ring model is not as clean in these modern processors as in the past, or as you might like. And again, we emphasize that this is all true for these really complicated pieces, such as the Intel x86 kind of processors, which are truly incredibly complex. But there are also much simpler processors that may not have any of this. So microcontrollers do not have, these, insane numbers of rings with all sorts of different modes and so on. They may be much simpler. Now that we've seen the security primitives and all the different ways that we have to handle isolation, so the rings and the paging and all of the other things, let's have a look at the other things that an operating system can do. The way in which we can harden the system to make sure that even if the code is buggy and contains vulnerabilities, that it becomes difficult for attackers to abuse the vulnerability or abuse the bugs and compromise our system. There are many different ways in which we can do hardening. Perhaps the best way to harden a system is to weed out all of the bugs. We would like to maybe formally verify that the operating system is behaving according to its specifications, assuming that we have correct specifications. But actually, this turns out to be very difficult to do for very large systems. We do have formally verified microkernels. For instance, the SEL4, the secure L4 microkernel, which was a fantastic effort by the folks at what was then known as NICTA, which is formally verified a complete microkernel and assures that whenever you have one process running on the microkernel, it can never access some other process's memory, for instance. Okay, but we cannot do this for very large systems, so we have to resort to other means. And the means that we're going to look at are information hiding, control flow restrictions, partitioning, code and data integrity checks, and anomaly detection. So the first technique that we'll look at is information hiding. And this is a very common defense that is now in most modern systems. And it's really simple. What we want to do is make it really difficult for attackers to access what they want to access, not by making it impossible, but by hiding it, right? So if you don't know where a certain important piece of information is in a 64-bit address space or a 48-bit address space, it becomes really difficult to find it. Okay, and this is known as address space layout randomization, ASLR. Okay, and in the kernel, it's known as kernel ASLR, KASLR. And that means that we randomize the location of relevant memory regions. So that is the most common implementation of ASLR. We simply randomize
the location of the stack, the location of the heap, global data, and text, so that it appears somewhere randomly in our 64-bit address space. And that means that if an attacker is able to control, say, the return address of a function or some other code pointer, it is not so easy for the attacker to determine which value to provide at that address, for that address, right? Because where are you going to make the program jump to, transfer control to? You don't know. You don't know the address of the interesting code snippet that you would like executed. Okay, and that's the idea of address space layout randomization. You make it difficult for the attacker to determine where to transfer control to or what data to read. Like I said, this is very common because it's very cheap. The overhead is very minimal. And so we find it in all the major operating systems. It was introduced by the PAC security team as a PAC security patch for Linux in 2001. And, all the other operating systems followed, within the years after that. Okay. Initially, this was only done at user space, so for the application, but nowadays we also have address space layout randomization in the kernel, where it's referred to, as I mentioned, as kernel address space layout randomization, KASLR. There are a number of important questions for address space layout randomization, and the first one, of course, is how random is random? Okay, how many bits of entropy do we have? If we randomize only, 2 bits in the address, it means that an attacker only has to guess at most 4 times to get the address right. If we have, 16 bits of entropy, 16 bits that we randomize, the attacker has a much harder time to guess the address that he wants to access. Okay, so the entropy matters a lot. The other important question is the granularity of the randomization. The way I described it earlier was that the address space layout randomization randomizes the base address of the code, the stack, the heap, and the data segment, and doesn't randomize anything inside of these chunks, right? That means that you don't know where the start address of the code is, but you do know once you've found it, you know exactly where each function is, because it's going to be exactly the same in every system. So regardless of whether it's randomized so that it's located at address 1000 on one system and address 50,000 on another system, you know that function foo will always be at the same offset from that base. So that is the granularity of the base address of a region, and that's the most commonly applied randomization. However, you don't need to do this. You can also randomize at a finer granularity. For instance, you could randomize at the page level, or you could randomize the order of the functions. Perhaps within a function, you can randomize basic blocks or even individual instructions. And finally, what you could do is change the registers that you use. Randomize the register users. So this is the more secure register allocator that will determine that, for this particular case, in this particular case, we'll use, this register that is available, and in a different randomized version, we use a different register for this purpose. Okay, so there are all sorts of choices that we have to make in terms of the granularity of the randomization. The other choice that we should make is, when do we randomize? So some systems, for instance Windows, randomizes at boot time. Okay, other systems, this is at load time. This is common in Linux, right? But we can do something more aggressive than that if we want to, right? For instance, we could do periodic re-randomization or constant re-randomization. So these are 3 important questions that we need to answer when we talk about address space layout randomization. How much entropy do we provide? What is the granularity of randomization? And when do we randomize?
Randomization can be done at the application level, which is where it was originally done, but nowadays we also have randomization in the kernel, known as KASLR. it's important to realize that it's kind of a baseline of defense, and it's available, but it doesn't actually stop advanced attackers. There's always ways in which you can leak the address of code or the address of data. Okay, and you can do that perhaps because there are pointers to these memory locations stored in memory, and if you leak those pointers, you also know where. I don't know, if you leak a return address in that is in memory, you also know where code is, right? So the return address is a pointer to code. Okay. So that is definitely one way of doing it. Sometimes the entropy that is used, certainly on 32-bit systems, the entropy that is available for randomization is simply too little. And finally, there's side channels that we're not going to talk about in detail that may help the attackers to break the randomization. However, it doesn't mean that randomization is not important. So a number of new defenses have been proposed that do not just rely on address space layout randomization, but use the randomization for building stronger defenses. So for instance, you may have some sensitive data that you use for your strong defense, your shadow stack, for instance, that is hidden by means of randomization, by having some small amount of data, sensitive data, at a random location in a huge address space. And as long as there's no pointers in memory that point to this sensitive data, you only use a dedicated register for this, it becomes difficult for an attacker to obtain this location. So randomization is by itself not a very strong defense. Perhaps more KASLR, kernel level address space layout randomization is perhaps more a defense against remote attackers than local attackers, because there's so many ways in which you can break address space layout randomization and obtain the mapping. But it's still an important defense, important building block for others.
So that was information flow hiding. What about other ways of hardening your program? Well, one particularly powerful way is to restrict the control flow, making sure that attackers cannot simply, divert the control flow in a program to any arbitrary location in the program code. Okay, so we want to make sure that all the control flow transfers, say the places that you return to or the places that you target with a call instruction, that they only land on the right places. Okay, and a seminal paper in that space is the CFI paper, the Control Flow Integrity paper that was published in 2005 by the people that you see here on the slide, and it's been extremely influential. Even though it was rejected a couple of times before it got accepted. Okay, but there's been a lot of follow-up work on making better CFI, attacking CFI, and so on. And it's what we're going to discuss next. So what's interesting about CFI is that most production systems, most compiler tool chains now have adopted control flow integrity into their tool chains, right? Typically, this is coarse-grained CFI, and we'll see what coarse and fine-grained means in a second. But it's still CFI, and it raises the bar for attackers. And that is because it's a really simple idea, and if you apply this in this coarse-grained manner, it need not be too expensive in terms of overhead. And the simple idea is as follows. We want to have a program executed, and we want it to follow only the legitimate branches and calls, the ones that we determined statically, that the developer intended. So we don't want to have arbitrary control flow in our program. We just want the control flow to follow the statically determined control flow graph. So we have a control flow graph saying that this indirect call instruction can target that function and that function, and so we want to ensure that it only targets those functions. And this function, say a string copy function, can return to this caller and that caller and that caller, but not to arbitrary places. That's what we're trying to enforce with control flow integrity. So let's consider an example. Here is array with and one what we want and hold only and only and all of the function calls using that's what we want. So again, this is what we want to enforce. We want to make sure that sort can only return to the call site in sort 1 or the call site in sort 2. So just after the call sites. Okay, and for this we need to instrument the code and insert a check to see whether or not it returns to the right thing. Similarly, we want to do this for other indirect branches and indirect calls. For instance, the use of the function pointer in the sort routine in the middle block. It should only be able to target less than and greater than. So we have to instrument that to have a check there whether or not the target is indeed less than or greater than. And the way we do that is by giving each of the targets a label, right? So less than gets a label 1, greater than gets a label 2, and whenever we do the indirect call, so the call with the function pointer, we check whether the target has the correct label. Is it either label 1 or label 2? Okay. Likewise, when we return from sort, we check whether or not the call site has the right label, right? So has it the label that corresponds to the call site in sort 1 or the label that corresponds to the call site in sort 2? Let's have a look at that in a little more detail. So here we see the same program again, but now represented in a slightly different way. It's more like a pseudo call graph. On the left, we see the sort 1 and sort 2 routines that call the block in the middle, which is a sort routine, which in turn calls via a function pointer either less than or greater than. And what we see is that we've added labels. We've added labels to the beginning of the less than and greater than functions, so at the entry points of these functions, because those are the functions that can be called with the indirect call, in other words, the call with the function pointer, and we add labels to the call sites so that we have a label for where a function may return to. Okay, so let's start with sort 1 on the left, and we see that there's a call to sort. Okay, and the call to sort will at some point after doing either less than or greater than, I forgot which, it will at some point return at the last instruction in the block in the middle in the sort routine. Okay, and we see that just before the return, there's a check now. The check checks the label of the target. It checks whether the address that we tried to return to has the appropriate label. Does it have the label ID11, which is the call site in sort 1, or the label ID21, which is the call site in sort 2? Only in those cases we allow this control flow transfer, and if not, we raise an alarm. Okay, so what about the indirect call? So if we have a call with a function pointer, we do the same thing. Just before the call, we check whether the function that we're trying to target has the appropriate label. So either label ID41 or ID51, corresponding to less than or greater than. We cannot target any other instruction in the program. Okay,
And finally, when either of these routines return less than or greater than, we again do the check. We check whether or not we return to the appropriate call site, namely the call site, so the instruction that is following the call in the sort routine in the middle. In other words, we check whether or not the target has the identifier we want. And if all of these checks are enforced, the attacker will have a hard time diverting the control flow to any arbitrary instruction. It can only target, legitimate call sites with returns and legitimate, functions with the indirect calls. Just like in information hiding, CFI also offers different options, different variants. For instance, there are different, options for the granularity. One option is to allow, for instance, an indirect call to target only a very small set of specific functions, right? So you have very precise labels, specific labels for every function that can be called. And then whenever you do an indirect call, you have to check whether the target address has a label that is actually appropriate for this particular call site. Okay? And if there's a long list of these labels, that check might be expensive. Alternatively, what you can do is to allow an indirect call to target any address taken function. So any function that could be used in a function pointer, right? So in that case, you only have to give all of these functions the same label and check whether or not we're targeting that particular label. Okay. And that means that you give a little more wiggle room to the attacker, because now the attacker is able to target any of those address taken functions, but it's much cheaper. So this is what we refer to as coarse-grained. And if we have individual checks and individual labels for each function that is address taken, then we talk about fine-grained CFI. Coarse-grained and fine-grained CFI. Now, coarse-grained CFI we now find in many systems, in browsers, in your operating system, in in both Linux and Windows. There are compiler toolchains that support this, so this is quite popular. Fine-grained CFI we don't actually see much in practice. Another choice that we have to make is whether or not we take context into account. So is our solution context sensitive or not? Okay, so the option one would be to allow the returns only to return to the actual call site from which this function was called, right? What we see on the saw on the previous slide is that the return was allowed to any call site that could call this function, right? So we could either return to the call site in sort 1 or to the call site in sort 2. Now, that is weaker, but also cheaper, again, to check. If we want to be more precise and more strict in enforcing control flow, we check whether or not we return to the one call site from whence we came. Okay, now we call this context sensitive. We also have context sensitive on the forward edge. For instance, in certain cases, you're only allowed to call a particular function. So there's also context sensitivity there. Don't want to go into this in too much detail. There are papers that have been published on this. I just want to say that for the back edge, so the return path, we can actually implement this with a so-called shadow stack. So that means we have a parallel stack next to our normal stack where we store, for instance, all our return addresses. Okay, and then whenever we do a return, we look at the shadow stack and check what the address should be that we're trying to return to, and then we only allow a return to that particular address. Okay, that means that even if your normal return address on your normal stack was corrupted, the attacker is still barred from returning to an arbitrary instruction in memory. Okay, like I said, current implementations that are super popular are offering coarse-grained CFI only, and sometimes they get combined with a fine-grained context-sensitive shadow stack. Now, control flow integrity protects only that, the integrity of the control flow. But there's more. There's also the data flow. And do we have any solutions for that? Well, at least there's some research on this where we try to safeguard the integrity of the data flow. Okay, and the idea, again, is simple. What we do is for every load instruction, so everything that obtains a value from memory, we maintain which store instructions may have legitimately produced that data. So for every load instruction, we try to identify which, according to the legitimate flow of the program, which store instructions that write to memory could produce the data that you're now using. And you make a table of that, and you maintain that. And then what you do at runtime, you maintain data for every byte in memory of the store instruction that last produces this data. So whenever you do a write to memory, you maintain for that memory location some data that says, okay, this write was done by this instruction. Okay, and then at load time, when you come to the load instruction, you check whether the tag, the label that was associated with the memory that you're trying to load was in the set of legitimate store instructions. Okay. Now, as you can imagine, this is relatively expensive, and at this point, to my knowledge, data flow integrity is not really used in practice.
A third way to do hardening is by means of partitioning. Partitioning is always good, and we've already seen this in previous slides when we talked about partitioning by means of memory protection and what have you. But we can do much more than this. So we can partition further. And one good example of this is what we refer to as data execution prevention, or write exclusive or execute, or annex, as it's sometimes the non-execute bit that it's sometimes called. All of these mechanisms are essentially the same, and it basically means that a page of memory is either writable or executable, but never both at the same time. And that has an advantage because it means that the attacker is not able to inject its own instructions in a program. You cannot overflow a buffer with your own instructions and then modify the return address and have your own instructions executed, because if you have written that data, you cannot execute this. So you enforce data execution prevention, essentially. And this is a very fundamental defense, which is extremely popular and now found in all of the popular operating systems that you find on PCs and servers and so on. Okay, so data execution prevention is one way of partitioning, the types of memory. Some of it you can execute, others you can write, okay? And never the two shall meet. Okay? Another way of partitioning is by making the boundary between kernel address space and user address space even harder. So you want to prevent the kernel from unintentionally accessing user space. Sometimes the kernel needs to copy data from user space, or copy data into user space. But this is sometimes also abused by attackers, or at least it has been abused in the past. So what you want to do is partition this such that the kernel can, in principle, unless it bends over backwards and sets the permissions correctly, it cannot directly access memory in user space, and it cannot execute code that is in user space. And this is known as supervisor mode execution prevention, SMAP, and supervisor mode access prevention, SMAP. Okay, SMAP and SMAP. So the kernel cannot execute instructions in user space, or the kernel cannot access data from user space. And this is, like I said, related to real attacks that are prevented in this way. If you want to know more about this, have a look at the documentation for SMAP and SMAP. Another great example of partitioning is what we now refer to as kernel page table isolation. And this is doing exactly what we said was not needed only a couple of slides ago. So we now remove the kernel from the address space of the user processes. Okay. And remember, we said we could do this because the user code cannot access the kernel memory anyway, because the page table entries for the kernel have the supervisor mode bit set. And that means that the user code cannot access this memory even if it wanted to. Now, unfortunately, the discovery of a new type of vulnerability in 2017, which became public in 2018, known as Meltdown, changed all that, at least for the Linux kernel, and caused the Linux kernel developers to remove the kernel from the address space of the user processes, leaving only a very thin layer in place to serve as a bridge between the kernel and the user space. Okay, and the reason why this was necessary was, well, Meltdown was this big goof up of the CPU vendors, where under certain conditions known as out of order execution, you would be able, as an attacker from user space, to provide a kernel address space in a read operation, and then under this out of order execution, it would actually fetch this data, and then you could leak that via a side channel. Now, I don't want to give a lecture on Meltdown or any other microarchitectural attack, but it did cause the Linux developers to remove the kernel from the user space processes address spaces. Now, why is that bad? Well, it's much less efficient, right? So the reason why the kernel was mapped in the first place was that this was a much more efficient way of doing this, because your system call became more efficient, right? So if you trap into the kernel, you no longer needed to do a full context switch and change the page tables, right, to the kernel's page tables, because you already had the kernel page tables in the same address space. But now, with this new kernel page table isolation, whenever we trap into the kernel from user space, we also have to change the page tables to the kernel page tables, and that is more expensive. Okay, so unfortunately, we had to do that, at least on the processors that don't have hardware mitigations against Meltdown. Another and somewhat related example of partitioning is partitioning of microarchitectural state, such as the caches. Okay. Now, unfortunately, on modern processors, there are many buffers and there's much state that is shared between multiple mutually non-trusting security domains, and the cache is one of them. We have level 3 caches that are shared between all the cores. We have, level 1 caches that are shared between the code that's running on a single core. And what that means is that we, as an attacker, may observe how our data is cached or not cached to learn something about what the victim, the other security domain, is currently doing. So if we all of a sudden see that some data that was in the cache before, our data that's in the cache before, is no longer in the cache, it means that the victim has accessed some data that maps to the same cache sets. Okay, and that sounds pretty innocuous, but in reality, you can actually build extremely sophisticated attacks from that and learn, things about, cryptographic keys and similar things. And again, I don't want to give a lecture on microarchitectural attacks or cache side channels, but it's a realistic threat, and the only way to prevent such a thing from happening is, you can, solve this in software and make sure that all code is always constant time. That's complicated. I don't want to say anything about that. But the root cause is that you're sharing these resources. So what you can do is not share the resources and partition them instead. And you can do this in hardware and software. So hardware, CPU vendors such as Intel have, Intel CAT, which allows you to partition the caches. But you can also do it in software by strictly controlling which pages you hand out to different security domains. So if your security domain has pages that map onto different cache sets than my security domain, we will never interfere as far as the cache is concerned. Okay, so unfortunately, you can do partitioning at the cache level, but it's much more difficult to do so at some of the other microarchitectural resources. For instance, the TLB and lots of other buffers that are in place, where partitioning is probably not possible or extremely difficult. And so what do we do in that case? Well, we can try to maybe flush these resources if we really care, but doing so would be very expensive. Anyway, let's move on.
Another hardening technique is to add integrity checks for the code and or the data. So what you try to do here is that you want to ensure that code and data is not modified. Okay, it can only have been provided by a trusted vendor. Windows, for instance, has relied on this for many years. The drivers are signed, so only signed drivers are allowed to run in the operating system. And what you can do is you can lock down a machine to make sure that all the code that is in there is labeled as trusted. To do so, of course, you need some secure boot process that tells you that this is code that runs only. This is a system that runs only trusted code. And the secure boot process is complicated. It starts with a root of trust, maybe some special hardware, and then that firmware initiates a sequence of stages, right? So the firmware loads the next part of the bootloader, say a bootloader, and that bootloader loads the operating system, and each stage verifies whether or not the next stage is indeed what you expect it to be. Right? So every time you verify the signature of the next stage before you load and execute it. Okay, so your firmware can check the bootloader can check the operating system can check the drivers, and so on. Now, by looking at a system, you don't really see whether or not it's securely booted. How can you tell? Okay. In order to be able to tell that, you need some form of attestation. And without going into the details of this, there are solutions for this. Many of them use special hardware, such as a trusted platform module. And the details are definitely beyond this presentation. There's a section on this in the knowledge areas. Finally, you can do integrity checks and runtime. So you can, maybe if you have a hypervisor, you can occasionally check whether or not the data structures of the kernel and the code sections of the kernel are still in order. Has there been any change in the code of the kernel? Has there been, is there any inconsistency in the data structures? So for instance, every time you get a call, so you actually have a VM exit where the operating system has to trap into the hypervisor can do a quick check to see if everything is still in order. Okay. Is the process list complete? Is there anything hidden in there? Is the system call table still the same? Is the interrupt vector table still the same? And a final hardening technique is to use anomaly detection. So this is different. Here we try to monitor the system for unusual events. The hypervisor checks whether or not the system is doing stuff that is different, unusual. Does it, for instance, crash more frequently? In which case, this may be an attacker trying to brute force some randomization. Anomaly detection is complicated because you have to be very careful that you do not classify something as an attack when it is not, because you might break legitimate applications. Okay, so you have to balance what we refer to as these false positives, so where you labeled something as an attack when it wasn't, and false negatives, where you're too permissive and you did not detect that something that was an attack is indeed an attack. Now, the security principles and security solutions in operating systems have been applied to many other systems also.
For instance, the same issues of security also appear in databases, where you have the same principles and the same design choices that we see in operating systems resurface. There's still authentication issues, privileges, access control, and so on. They're exactly the same concerns. And the solutions are also sometimes very similar, sometimes also a little bit different. I don't want to say too much about this in this lecture. It's not really the core of our concern, And if you want to know more about this, well, there's a little bit more text about this in the text of the knowledge area itself, but it's really part of the database design and implementation. Our final topic concerns the adoption of security solutions. Surely by now, everybody has seen so many horror stories in newspapers about data leaks and security breaches that whenever anybody proposes a new solution that improves security, people must be jumping up and down about this and adopt this immediately. Sadly, this is not the case. It turns out that getting your security solution adopted is a real challenge. Mind you, these attacks are getting increasingly sophisticated and therefore require increasingly sophisticated defenses to stop the attacks. Now, these defenses typically do not come from the operating system developers themselves, but often from external teams. And there's a tension often between the external teams and the kernel developers. Okay, they're not as eagerly adopted, even though everybody's convinced that the security problems are real. They're not as eagerly adopted as you might think, and there's several plausible reasons for this. Okay, and the most obvious reason is that nothing is for free. Every time you add one of these defenses, your system becomes slower. There's always a price to pay for security, and the question is, what is an acceptable price? The other question is, are my customers still going to buy my system if it's slower than the competitor, only because I added this feature that hopefully will never be needed, right? Because hopefully will never be attacked. So it's much easier to sell performance than it is to sell additional features that may improve your security. And I say may because that's the other problem. It's very hard to measure how much extra security you buy with a particular defense. Okay, how much more secure will we be? And that means that the trade-off between security, additional security, and performance is very unclear. So what we should do in research is focus on the defenses that significantly raise the bar for the attackers, make it really more difficult to compromise the system without incurring too much overhead. Right? It should still be acceptable. And what is acceptable is, not always clear. It very much depends on who you ask. But in industry, it's typically considered to be only a few percent at best. Okay, so that means that there's not a lot of computation that you can do extra to secure the system. But most importantly, you also have to somehow show how much extra security that performance hit is going to buy you. And that is typically a problem. In conclusion, we have seen that the operating system and hypervisor are the lowest level of the software stack, and therefore the most privileged components, and therefore they play a critical role in security. They are the bedrock on which all other security solutions are built. Unfortunately, their attack surface is quite large. They can be attacked from multiple sides, processors running on top of them, or attackers on the other side of the internet sending packets towards your machine, or malicious devices. And moreover, they can be exploited using traditional software bugs, buffer overflows, and other memory corruption attacks, as well as more low-level microarchitectural attacks where they use cache side channels or meltdown and other kinds of attack to access data in an indirect way, typically using side channels. Okay, because they are so fundamental to the security of the overall system, we often discuss things at the operating system and hypervisor level in terms of very fundamental security principles and also access models. And what we have seen is that the security of our system is typically influenced by the design of the operating system. Is it heavily partitioned, or is it one monolithic blob? But also the available security primitives in hardware and software, and the mechanisms that are used to harden our software. And with that, we've reached the end of this presentation. I hope you've enjoyed the explanation, and I encourage you all to read the text that corresponds to this knowledge area. Thank you.